The topic of this video is dimensional analysis. Dimensional analysis is a tool that lets us solve complex problems involving multiple components and units. It allows us to multiply expressions, numbers with associated values and units, together to arrive at a simple answer from a seemingly complex question. For practical purposes in chemistry, we use dimensional analysis to convert units of one item into units of another using conversion factors. In the diagram to the right, we have several base units of the metric system that we see on a regular basis when working in the sciences. Several of these standard units and what they are used to measure are listed here as well. The standard units used to measure mass is the kilogram, length, the meter, time, the second, etc. Dimensional analysis lets us readily interconvert between units. Let's start with something basic that you can probably do in your head. We know in 1 minute there are 60 seconds. And this can be expressed in writing as 1 minute divided by 60 seconds. Because these conversion factors are interchangeable, we can also flip this and write this conversion factor as 60 seconds in 1 minute. Even though the way the conversion factor is written has been inverted, they represent the same information. The same is true for how we know in 1 hour there are 60 minutes. This can be written as 1 hour divided by 60 minutes, which can also be flipped to be read as 60 minutes divided by 1 hour. Again, because this conversion factor remains the same, we can simply invert it depending on how we want to use it. Lastly, the same is true for how many hours are in a day. We know there are 24 hours in a day, and this can be written either as 1 day divided by 24 hours, or 24 hours divided by 1 day. Now let's put this to practical use. Dimensional analysis lets us readily interconvert between units, as I've said. Let's start with something basic that you can probably do in your head, by using dimensional analysis to find how many seconds there are in 3.5 minutes. We can start with information we know. We have been asked to find how many seconds are in 3.5 minutes, so let's start here. We know our answer has to be in seconds, so we have to convert minutes to seconds using our conversion factor on the right. When we multiply these values together, our units, in this case minutes in the numerator and denominator, cancel out, and we are left with only seconds in the numerator, along with the value of our arithmetic, 3.5 times 60. Thus, we have solved the question, how many seconds are in 3.5 minutes? 210 seconds. What if we want to find out how many seconds are in 27.5 hours? This may seem daunting, but let's break down the question. Let's start with information we know again. We have been asked how many seconds are in 27.5 hours, so let's start there. If we use our table to the right, we will see we do not have a direct conversion from hours to seconds. So we can start by converting hours to minutes using the conversion 60 minutes in 1 hour. When we multiply these together, our units cancel again, and now we are left with minutes in the numerator. However, we are trying to arrive at an answer in seconds. Fortunately, as we used in the last problem, we have a conversion factor to convert minutes to seconds. Using this conversion factor again, we can convert our minutes to seconds by multiplying where we are. By 60 seconds over 1 minute, this time our minutes cancel out and we are left with seconds in the numerator. If we perform our arithmetic 27.5 times 60 times 60, we arrive at 99,000 seconds. So using dimensional analysis, we successfully broke down a complex math question into smaller parts, and by using a series of steps and conversion factors, we converted 27.5 hours to 99,000 seconds. So how about converting metric units with expressions like kilo or milli or micro? The conversion table to the right is a handy tool to remind us how many of one amount of units converts to the total number of the same units with a different prefix. On the left of our table here, we have our prefixes. In green are common prefixes used in scientific practice, such as kilo, milli, micro, nano, and even pico, or pico. In the center are the conversion factors to convert these. For example, if we want to talk about mass and convert kilo units to standard units, in every 1 kilogram there are 10 to the third, or 1,000, grams. Because this is a conversion factor, we can swap these numbers, and this can be written as for every 1,000 grams, there is 1 kilogram. Similarly, if we want to convert standard units to microunits, and we are measuring volume, for every 1 liter of a substance, there are 10 to the 6th, or 100,000 microliters of the substance. This can be flipped and rewritten as 100,000 microliters in 1 liter. Lastly, if we want to convert milliunits to microunits, and we are talking about the quantity of particles, whether that be atoms or molecules, we know in every 1 millimole there are 10 to the 3rd, or 1,000 micromoles. And if we flip this, we can see that for every 1,000 micromoles of a substance, there are 1 millimole of that substance. Let's try interconverting something a little more complex than just time. Let's move between different units. I like to go fishing, and I do a lot of ice fishing in the winter. One cool toy I wish I had was a Garmin LiveScope fishing sonar system, and if I could, I would buy 2 of them. So, using dimensional analysis, let's find out how many hours I would have to work to purchase 2 of them. This means we are going to convert fishing sonars to hours of work. With a complex problem like this, let's break it down and start with information we know. We are given several conversion factors on the right, such as 1 sonar costs $3,000. In the average week, I make $500. And in the average week, I work 52 hours. We know I want to purchase 2 sonars, so let's start there. We are given a conversion factor that 1 sonar costs $3,000. However, if we try and multiply 2 sonars by 1 sonar divided by $3,000, we will not convert units and instead be left with a value of sonars squared in the numerator and dollars in the denominator. Remember, we can invert a conversion factor because the relationship between them stays the same even if inverted. So instead of using 1 sonar divided by $3,000, let's use $3,000 per 1 sonar. This will allow us to cancel sonars out as a unit, and we are left with dollars in the numerator. Next, we don't have a direct conversion for dollars to hours, but we can convert dollars to weeks using the conversion factor of every 1 week I make $500. Our dollar units cancel now, and we are left with weeks, which we can convert to hours using the conversion factor 52 hours per 1 week. This allows us to cancel out weeks, and we are left with hours in our numerator, and if we perform our arithmetic of 2 times 3,000 divided by 1, times 1 divided by 500, times 52 divided by 1, we are left with 624 hours. I would have to work around 624 hours to purchase 2 fishing sonar systems. For practice purposes here, we are ignoring significant figures. Now to use dimensional analysis to solve a seemingly complex chemistry problem involving multiple information components. Remember, dimensional analysis allows us to multiply expressions, numbers with associated values and units, together to arrive at a simple answer from a seemingly complex question. Let's try and find how many atoms of carbon there are in 10 milliliters of graphite. Remember, graphite is composed of carbon and therefore has a molecular mass of 12 grams per mole, which is given to us on the right. Let's start with our 10 milliliters of graphite. We know the density of graphite, which relates or converts volume to mass, is 2.266 grams of graphite per 1 milliliter of graphite. Again, this is given to us on the right. If we multiply 10 milliliters of graphite by 2.266 grams of graphite per 1 milliliter, we can cancel out our milliliters and we are left with grams. Now to convert grams to moles. We invert our conversion factor of 12 grams per 1 mole, which allows us to cancel out grams of graphite, leaving us with moles graphite in the numerator. And if we use Avogadro's number, which states that for every 1 mole of a substance, there are 6.022 times 10 to the 23rd particles of it. So by multiplying our value by this conversion factor, we are left with atoms in the numerator. If we perform our arithmetic, we find that there are 1.14 times 10 to the 24th atoms in 10 milliliters of graphite. This demonstrates that by using dimensional analysis, we can find simple answers to very complex questions when given or using the right conversion factors.